There we go. Thank you very much, Robert. I'm delighted to be back in Princeton again. The Institute will always have a place in my heart, and especially the walks in the woods I often took with Vladimir when we were pondering various matters. There's his homepage. He was very methodical about keeping record of what he did for his legacy, and he was very exacting about it. But since he died, we've taken the files from his computers and put them on a memorial website almost adjacent to it, where people can access his unpublished works and his works in progress. Here's the course of his life, which was sketched by Robert. You can see he only spent 1 year teaching at a university. And you can see he tended to work on more than one project at a time. For example, he started thinking about computerized proof in 2002, as we'll see. So there's the poster for the Memorial Conference. I hope you've all seen the poster. You can even get your own copy of it from the table in the lobby. And it might be a little bit hard to notice, but there are two formulas in the background of the poster. And there they are. And these two formulas represent the two phases of his mathematical research: motivic homotopy theory and univalent foundations. The first one is the statement of the Bloch-Kato conjecture, and the second one is the statement of the univalence axiom. So what I want to do in this talk, which is aimed at a general audience, I hope it to be understandable by non-mathematicians. So I will be saying some things that are a little bit inaccurate mathematically. And mathematicians will see little asterisks at those points, so they don't have to tell me that I know I'm saying something inaccurate. But I'm trying to sketch it a little more poetically than totally accurately. So first, what about the Bloch-Kato conjecture? What is it? Well, it's a formula. It's a formula that says two things are the same. There's that thing in the middle, which means more or less equal or equivalent, and then there's something on the left-hand side and there's something on the right-hand side. And the things on both sides are sort of complicated and technical, so I'm not going to say what they are, except for the lowercase k, which is a system of numbers considered in an abstract way, what's known in mathematics as a field. And of course, there's a hypothesis for this theorem too. But the two sides are algebraic. The two sides of the equation come from the domain of algebra, and the domain of algebra consists of studying what happens when you add and multiply, subtract and divide. So if you look at the K-theory preprint archives, which is where Vladimir started posting his papers before publication, starting in 1994, which was when we set up the K-theory preprint archives. Rick Jardine and I, Rick is here. You see that he had a flurry of papers to post on the same day in November. 5 papers were posted. And then papers kept coming out. And it was really an exciting time to see the advances he was making. Look at the 5th one from the bottom. It's joint with Andrei Suslin, and the second one from the bottom is joint with Andrei Suslin. It's very sad that Andrei Suslin has also died recently. During the summer, he died at the age of 67, but he was a formative influence on Vladimir and collaborated with him on a lot of work and provided an audience to check his results and the details of his proofs. But you can see there are other co-authors. Fabien Morel is here. Eric Friedlander is here. And Chuck Weibel is here. So he announced it in a preprint in December 1996. He announced that he had a proof of the Milnor conjecture. And there it is. It looks just like the formula I put up there, except that instead of the letter L, there's the number 2. And then finally, in 2011, in the Annals, he published the general case. And it depended a lot on the work of other people. One should mention especially Marcus Rost's ideas having to do with constructing norm varieties, and Andrei Suslin and Zhukovitsky, who put the details of the construction in print, and Vladimir was able to refer to that in this paper. And Chuck Weibel, who provided an alternate approach toward the final securing of this theorem. So what is the thing about? Well, algebra is about, as I said, multiplying and adding, and also about equations. And so if you take an equation like x squared plus y squared equals 1, you get the circle. That's an example of something studied in algebraic geometry. Algebraic geometry consists of studying geometrically the solutions of algebraic systems of equations. And as you raise the number of variables and the degrees of the equations, you get things more and more complicated, but still there's some fruitful avenue toward looking at these things algebraically. And what is especially notable in the broad course of mathematics for the last 120 years is that the connections that have been formed between topology and algebraic geometry. So I'm now going to explain what topology is, and the point is that there's a broad thrust in the history of mathematics about bringing techniques of topology into algebraic geometry. And it's hard to do because that little k, that abstract system of numbers, is not like the real numbers. In this picture, the numbers x, y, and z that give the coordinates of the points on the surface are real numbers. So what happens when you consider x, y, and z to be drawn from something more abstract, some more abstract kind of number system, which is completely unfamiliar to the real numbers? That's what Vladimir and many previous mathematicians, including Riemann and Grothendieck, were concerned with. So what is topology? Well, it's almost a trope on the web that a topologist doesn't distinguish between a coffee mug and a donut. And I found this on Wikipedia, this animation, and it illustrates the point pretty well, that by a continuous deformation or by a movie, you can get from the coffee mug to the donut. And what are the rules for such movies? What movies are allowed? Well, there should be no puncturing, there should be no tearing, there should be no cutting. But what if you take those rules seriously? Here's another movie that has no puncturing, no tearing, no cutting. But something of dimension 3, the solid donut, drops to something of dimension 1, the ideal circle. So is it allowed? Well, one can choose to allow it, and this is what's done in homotopy theory. The donut and the circle are homotopy equivalent. So that's the basic notion of homotopy theory, and that's the field Vladimir was an expert at bringing into algebra. If we cut the donut radially, we get a disk, and we can watch the same movie as the disk shrinks to a point. And if we assemble all the frames of the movie into a single object, and remember for each point of each frame what time that frame appeared at, we get a single geometric object together with a function, drawn in a red arrow, that associates to each point in each frame the time at which that point appeared. And so the black line at the bottom is the time axis. And if this function has the property that the slices above, the frames of the movie, don't amount to tearing or cutting or slicing or puncturing the shapes above the points, then this is what's called a fibration. You don't need to remember that word. But it's a basic concept in homotopy theory. And now what about the topology that Vladimir did? Well, actually, what he did both in motivic homotopy theory and in univalent foundations and homotopy type theory deals with a more combinatorial incarnation of topology, where instead of considering those smooth surfaces, which have to be described perhaps in infinite terms, you think of your topological shapes as being composed of points, line segments, triangles, and so on, so that you can describe the essential topology of the surface or shape by giving no information about the distances or the lengths of the sides or the sizes of the triangles or the angles in the triangle. You just give names to all the triangles, give names to all the edges, give names to all the points, and tell which triangles have which edges as their 3 edges, and which edges have which 2 vertices as their 2 endpoints. And so that's, since a higher dimensional triangle, well, in 3 dimensions is called a tetrahedron, and in higher dimension it happens to be called a simplex. And so the word simplicial appears in his papers many times. And so he was expert at combining that world of combinatorial simplicial topology with the world of algebraic geometry. So here I put up again the picture of the circle given by the equation x squared plus y squared equals 1. And here is a combinatorial simplicial way of describing a topological circle. Triangles are not needed because a circle has dimension 1. So it suffices to put line segments in a row and say what their endpoints are. And so now the world of motivic homotopy theory that Vladimir invented is a world where the topology exists side by side with the algebraic geometry in a peaceful coexistence that allows stronger theorems to be proven. And so both types of circles are present, and there are different types of circles. It turns out these circles are not the same type of circle. And from circles, you can build higher dimensional spheres. And these give rise to higher dimensional spheres in this new world. And you can count how many of the algebraic circles you use in building a sphere and how many of the topological circles you use. And those 2 numbers have something to do with the theory. So it's a different world from what happens in algebraic topology. Since 1900 or so, people have been investigating topological invariance of surfaces and trying to make precise the definition of what a hole is. And that pursuit is presented to a topologist in a startlingly different way, and so it has to be dealt with. There's more topology that comes up in this pursuit. Already in algebraic geometry, various topologies were considered, especially by Grothendieck in school. The Zariski topology, the Étale topology, and the Nisnevich topology. These things all have to do with figuring out, in a very vague way, what it means for 2 points on the circle to be close to each other when all you have is algebra to deal with. And, you know, when you have algebra to deal with, I should point out that you might think at first that sine and cosine give you a way of telling when 2 points are close to each other, because if you have an angle theta, you can take the cosine and the sine and call those x and y and get a point on the circle. But sine and cosine are not obtained from the angle by adding and multiplying in any finite way. And so they're not part of algebra. And so something else has to take their place, and it's a much more interesting world. And I put up this paragraph from one of his papers, no, from his thesis rather, because somehow it seems to me like poetry. The most important cause why the topologies usually used are not satisfactory for our purposes is that they are all too weak. Let me explain what I mean. The only cause why we are to use the topology and sheaves in the homotopy theory is the absence of the direct limits in the category of schemes which we need to define such objects as cohomomorphism, suspension, or realization of a simplicial scheme. And skipping a bit. Therefore, it is natural to try to find the topology such that the direct limits of such kind would be representable by the corresponding direct limits of sheaves. Well, to me, this shows his bravery and his intuition, and it just seems like poetry to me when he introduces 3 more topologies that are stronger than the first 3 I listed, and it led a commenter that I quoted in the obituary in Nature to say the following. In Voevodsky's motivic homotopy theory, familiar classical geometry was replaced by homotopy theory, a branch of topology in which a line may shrink all the way down to a point. We've seen that in the videos. He abandoned the idea that maps between geometric objects could be defined locally and glued together, a concept that Grothendieck considered to be fundamental. And a colleague commented that if mathematics were music, then Voevodsky would be a musician who invented his own key to play in. And he was referring to these 3 topologies, which are of a novel type that dispense with the notion that maps can be defined locally. So there he is in Beijing, being presented with the Fields Medal, along with Laurent Lefort by Jiang Zemin, the president of China at that time. And there's Christophe's introduction to his laudatory paper written for the proceedings of the International Congress, Christophe Soulet. He has demonstrated an exceptional talent for creating new abstract theories about which he proved highly non-trivial theorems. He was able to use these theories to solve several of the main long-standing problems in algebraic K-theory. This field is completely different after his work. He opened large new avenues, and to use the same word as Lomont, he's leading us closer to the world of motives that Grothendieck was dreaming about in the 60s. I think that's right. Algebraic K-theory is my field. I'm not truly expert on Vladimir's work in motivic homotopy theory. But I do know that in the 80s, Merkuriev and Suslin made a big splash when they proved a special case of the Bloch-Kato conjecture. And Vladimir was grateful to Suslin for teaching him the techniques from that paper. And Merkuriev is here also at our conference. So that's part 1. That's how I intended to take a look at algebraic geometry. Part 1.5 of the talk is an interlude. I consider it amazing that Vladimir was the sort of genius that would not be tied down. He would not be confined to a single research area. So notice that this announcement of the proof of the Milnor conjecture was in December of 1996, and that was just a preprint. It has to get published. The details have to be verified. 4 or 5 or 6 papers have to be written yet to make the result secure. But then in September of 1997, he started working on artificial intelligence as soon as he moved into the math department, math building at Northwestern University. And he sent me a program he wrote in C. It was the first computer program I saw that he had written. But it turns out he had, as he told me later, he had experience programming computers. He had some sort of job in Moscow as a computer programmer, maybe even before he was an undergraduate or during his undergraduate years. But what he got interested in was artificial intelligence and doing experiments in the computer for seeing how some very naive creature, which he called a rat, could navigate a maze. So the black represents the creature. It starts here, and the trace goes around the world and runs into occasional obstacles that are in red. And so he wrote and modified this program and spent hours and hours looking at how the creature would learn. And then he got interested in robotics. And he asked me whether anyone was doing robotic locomotion. And he was interested especially in how the brain of a creature that finds itself in a body, which it hasn't seen before at birth, can learn how to walk. So he wanted to figure that out. Now, another part of the interlude comes after his appointment at the Institute. Oh, does anyone know? I was going to go look over in the basement of the dining hall and see whether the photos are on the wall still. No, they're gone? Well, there might be there. In any case, there's a chance that many of his beautiful photographs of nature are still on the wall downstairs near the dining hall. So go into that nether hallway if you get a chance and take a look. He said later that the way you get these photographs is by incredible patience. He would take his camera and sit in the woods for hours and hours and just wait. And then something good would appear. So he also got interested in mathematical biology and was very happy about it because he thought he was discovering lots of new things, especially about how to apply mathematical concepts to the problem of predicting the problem of deducing the genotypes in the past of a population about which all you know is today's phenotypes. And so he had this big theory, and he wrote 2 papers. This is the second one of those. These papers were never released to the public. It turned out he considered them failures, as he revealed later in an interview with Roman Mikhailov. The whole project was a big failure. It was the biggest failure of his life. And although he did learn something about topology, about probability theory and how to apply the notion of groupoid to it. Anyway, those papers are on the Memorial website in archival form. So you can take a look at them. And now what about part 2, the univalence axiom? So what's the motivation for him? In 1999, at the IAS, I was giving a series of lectures, and Pierre Deline was taking notes and checking every step of my arguments. And it was probably a great service that Pierre rendered at that time, paying attention to these very technical things, because it made Vladimir pay attention and divert his gaze from artificial intelligence. Only then did I discover that the proof of a key lemma in cohomological theory contained a mistake, and that the lemma as stated could not be salvaged. Fortunately, I was able to prove a weaker and more complicated lemma, which turned out to be sufficient for all applications. A corrected sequence of arguments was published in 2006. Here's the 1994 version of the lemma, side by side with the 2006 version of the lemma. So if you scan the symbols, even if you don't understand the words, you can see that the letter U, the capital letter U, is appearing in 2 ways in the bottom version and only in 1 way in the top version. Once with a subscript 0 and once without. And that's the complication that he had to introduce into his lemma to get it to work properly. This story got me scared. Starting from 1993, multiple groups of mathematicians studied the cohomological theory paper at seminars and used it in their work, and none of them noticed the mistake. And it was not an accident. A technical argument by a trusted author, which is hard to check and looks similar to arguments known to be correct, is hardly ever checked in detail. This is right. Even the referee of a mathematics paper doesn't have time to check everything. I used to, when I was younger and had much more energy to spend refereeing, I used to be able to invest 20 hours refereeing a typical paper and trying to check for mistakes. And that would never suffice to check the entire paper. And so I'd write to the editor and say, well, I checked sections 1 and sections 2, and if the other sections of the paper are like them, then it's probably correct. So Vladimir felt strongly that something should be done and that the mathematical literature should be checked for soundness with the aid of a computer. And keeping in mind that timeline, notice this email that he sent to me in 2002. I'm thinking again about the applications of computers to pure math. Actually, I don't know when was the previous time. Oh, maybe it was the artificial intelligence. Except that wasn't pure math, that was applied math. So I don't know what again means. It must have done something before. Do you know of anyone working in this area? I mean mostly some kind of a computer language to describe mathematical structures, their properties and proofs in such a way that ultimately one may have mathematical knowledge archived and logically verified in a fixed format. At this time, he wasn't aware of type theory and what the type theorists were doing. I visited him in 2004 and we brainstormed about this, and ultimately our ideas didn't go anywhere, and ultimately he did find out about type theory, and that's what got the whole thing jump-started. He could have, for example, at this time, he could have seen, but didn't, the paper of Audi and Bauer, where they explain what to do about mathematical propositions in type theory. So I didn't hear from him for a while, and then suddenly in 2006, I got this 7-page preprint with no bibliography, which was completely opaque to me. I had no idea what it was about. And it looked good, but I couldn't tell. Notes on homotopy lambda calculus. So that's his first name for the theory. That name was discarded. Now one speaks of homotopy type theory, or one speaks of univalent foundations. But you can see section 1 of chapter 2 there is about univalent maps. So I already had the idea that this idea of univalence is one of his first ideas. And he doesn't consider it his greatest idea. I'll say later what he considered his greatest idea. But let me try to give the mathematical flavor of univalence. So there's the univalence axiom on top that he's famous for. And it turns out that there's a way of viewing that axiom in topology. Now, let me explain why one would want to view some statement of mathematics as a statement of topology. Well, when you enter the theorems of mathematics into the computer, you'll be using some sort of formal language. It'll be like a programming language. It'll be like C or Fortran or something like that. And the programming language will have rules. And the rules might be ridiculous. The rules might allow you, for example, to prove that 1 + 1 is equal to 3. And you can't tell by looking at the rules whether 1 + 1 = 3 will ever be a conclusion of the rules you've chosen. And in particular, this univalence axiom was going to be one of the rules he was choosing. And so he needed a way of checking that it's sound, that its introduction into the theory doesn't lead to some sort of contradiction like that. So what was it? Well, he needed a way to view the formal language in topology. And he needed to prove a theorem that no formal proof in the formal language would ever prove something absurd. And topology would be the means for doing that. And the first thing would be univalence. Let me see what my next slide is. Yeah. Why did he want univalence? He knew from the beginning that it'd be very important to correlate the results of different authors who are formalizing things in different ways. If you have one author giving one definition of triangle and another author giving another definition of triangle, but they turn out to be equivalent, then you would want the theorems of the second author to be usable by the first author, and conversely. So you want some sort of mechanical way of transporting theorems between equivalent situations for maximum versatility. So what he had in mind here from the start is building a huge repository of mathematical theorems and their proofs, and using that to build on forever, using that as a daily aid to mathematicians in their research, so that today they are not nervous about what they proved yesterday because they also formalized it in the computer. And also in order to relieve referees of the responsibility of spending more than a minute checking the validity of proofs. The best journals would be able to have referees comment just on the interest and the beauty of the proof. So what's needed is some sort of way to promote equivalences to something that can be used in the logic of the language to transport theorems between equivalent situations. So here is the statement of the univalence axiom. On the left side, we see x equal y. Just think of x and y as situations, so they're actually types. But think of them as situations, and think of x equal y as being something from logic that says that x and y are the same, or at least can be identified with each other. And on the right-hand side, oops, wrong button. On the right-hand side is, in parentheses, is the statement that x is equivalent to y. So that's what I've been talking about. And then in the middle, between those two parenthesized expressions, it says that equality is equivalent to equivalence. In other words, if you have an equivalence between x and y, then by going from right to left, you can promote that to an equality between x and y. And the rest of the formal language is set up in such a way that when you have an equality between two types, then the theorems can be transported automatically and simply. So what's the topological justification for it? Well, the topological justification is this. On the left side, we have that movie I showed before, connecting the three-dimensional donut with the one-dimensional circle. And I said at that point that the two things are homotopy equivalent. But one thing I didn't tell you was that the definition of homotopy equivalence in a homotopy theory course in a graduate math department does not deal with movies like that from the beginning. Instead, there's a more static definition of homotopy equivalence, which consists of putting the two shapes side by side and postulating the existence of two functions, which I've indicated in red, going in opposite directions. The function associates every point of the circle to a point of the donut and associates every point of the donut to a point of the circle. And then there's some relationship between the two functions, which I'm not going to go into. But that's the definition you get in the topology course. So what about this movie thing? Well, somehow it's amazing that topologists never ask the question whether any homotopy equivalence could be realized in such a way that the two shapes were the first and last frames of the movie. And so Vladimir asked Peter May, and Peter May asked Pete Bousfield, who's at University of Illinois at Chicago, and Pete thought about it for a while and came up with an argument. And so there's the email in May of 2006. So Vladimir had this argument in hand, but his genius was in realizing that he could use this for securing the soundness of the logical system he was about to develop. And finally, he was ready to reveal it to the world in 2010. So he gave a talk at CMU where he talked about it. And the word univalent appears again. And, well, he calls it the equivalence axiom here. Later it was called the univalence axiom. But look in the quotation marks. Two homotopy equivalent types are equal. That's what we're talking about here. I should have said what types are. In computer programming, there are types. When you introduce a variable in the C language, for example, you have to say whether it's going to be an integer, whether it's going to be a string, whether it's going to be a character, whether it's going to be a floating point number, what kind of thing it is. That's called the type of the variable. Well, the same thing happens in mathematics. When you introduce a letter like x, you say x is a triangle, or x is a curve, or something like that. And so in mathematics, it's very natural for things to have types. And that's why type theory should appeal to mathematicians immediately, because in set theory, one doesn't segregate things into types at the level of logic, only at the level of human understanding. Humans understand that a triangle is not the same type of thing as a curve, but set theory just sees everything as a set. So univalent foundations, here's the Wikipedia page on univalent foundations. They're an approach to the foundations of mathematics in which Mathematical structures are built out of objects called types. Types in the univalent foundations do not correspond exactly to anything in set theoretic foundations, but they may be thought of as spaces, with equal types corresponding to homotopy equivalent spaces and equal elements of a type corresponding to points connected by a path. And then Vladimir goes on to say what old Platonic ideas of Grossman and Cantor inspired these things, but I don't think that's true. I think he looked for underpinnings in the older literature after he had the ideas himself. He wanted this to follow some tradition, and he found traces of it in the literature. And so one can look in these works and see what he was talking about. So one of the things he did, using his previous experience as a computer programmer, was to start formalizing theorems using the computer program Coq, which is based on the type theory of Martin Löf, and which is based on the calculus of constructions of Thierry Coquin, who is here as an organizer. And this was incredibly important for the field, for him to formalize the facts. It's not enough to just present mathematicians with a formal language and say, here, use this. I've proven it's sound. What you also have to do is you have to tell the mathematicians how the ideas of mathematics can be expressed in the language. Because the language doesn't contain things like group, ring, triangle. It's up to you to build those things. And you have to be shown how, and you have to be shown that it's feasible. So he wrote code. He spent 3 months writing code, and it was an incredibly successful effort. And here's the way the univalence axiom looks in the code. T1 and T2 are replacing X and Y. Well, maybe I have another thing. Oh, yeah. And then it says that the eq-weak map, whatever that is, which goes from T1 to T2, is a weak equivalence. So is weak, ISWEQ, that's the notation for that equivalence symbol that was between the two parenthesized expressions before. So if you look earlier in the code, you see his definition of equivalence. A function is an equivalence if for each y and y there's just one x with f of x equals y. And this has to be interpreted with equality in this rarefied formal language of type theory. So there's notation for being an equivalence. It's that notation I had on the screen before. I put a little equal sign with a tilde above it. And the type of all equivalences can be denoted that way. X is equivalent to Y. And then there's the univalence axiom again. So it's fairly simple to state, and it turns out he was enormously successful in applying it. But first, let's take a look at what he regarded was his main accomplishment in this area. He thought the univalence axiom was not important as the notion of homotopy level or H level, which he introduced. So here's the code for it. There's no point in you trying to read the code. Let me just explain what it means. So he envisions types as mathematical objects. There would be the type of natural numbers, the type of triangles, the type of algebraic varieties, and he divides them up into a hierarchy. And the hierarchy is classified by this number, the H level. And so at level 0, there's just one type, essentially. It's true. And then at level 1, we refer to truth in making the definition of the word proposition, as Awadi and Warren did in 2000. Awadi and Bauer did in 2002. Proposition is a type, so that I should have said first, more clearly, that a type has elements. A type is like a set. A set is considered a collection. It has elements that belong to the collection, and a type is like that too. So types and elements come hand in hand in the language. And so in this table, we consider various sorts of types T, together with various pairs of elements, R and S, although the names will change. And then we consider the identity type between those two elements. And this is also a novel feature of Martin-Loeff's type theory, which was invented in the 70s, is that equality is a type. That's all it is. So definition, a proposition is a type, so that whenever you have two elements of it, P and Q, then P equals Q is true. And these elements of a proposition might as well be called proofs. And if you think back to how mathematics has been done over the centuries, a proposition is stated, and then a proof is given, and the proof is present only to establish the proposition's truth. And strictly speaking, one doesn't need to refer to the proof later on. And one also expects and knows that when one uses a proposition to prove something else, one always gets the same answer regardless of what proof was given for the proposition. So propositions and their truths are usable without regard to which proof was given, and that's the important point. And this was realized early on. But then Vladimir's invention was to define a set to be a type where any two elements of the set have x equal y being a proposition. And this recovers the world of set theory. The world of set theory was based on propositional logic. All men are mortal. There's truth, there's falsity, there's conjunction, disjunction, implication. And equality in traditional mathematics is always a proposition. And so we recover that by fiat. We just say we're going to talk about types that are sets, and so they have this property. But then there are types of higher level. A type of H level 3 would be a type where any two elements have A equal B being a set, and not all of them being propositions. And similarly for H level 4. Any two elements of them have the identity type or equality type being of H level 3. And so this hierarchy is what he thought was fundamentally more important than the univalence axiom, because it opens up a world of wonderful mathematical objects which are invisible when building mathematics on set theory. It's just a new world of mathematics. And these types of higher level can be studied in their own right, and they're not visible previously from the point of view of set theory. So one can imagine that if univalent foundations replaces set theory as a popular foundation for all of mathematics, that these types of higher level will be important in their own right as mathematical objects for everyone to study. So what he demonstrated in his foundations repository was the formalization in this computer program of a bunch of facts, which are reassuring to mathematicians. Functions whose corresponding values are all equal are equal as functions. This is something mathematicians expect. This followed not by assuming it as an axiom, but by proving it from the univalence axiom. The type of functions from one set to another is a set. Mathematicians would insist on this. The type of all subsets of a set is a set. Well, there's an asterisk there. That's a warning to the mathematicians in the audience not to argue with me at this point. There's something tricky about that, which is sort of unsettled in the semantics. But let me just apologize to the non-mathematicians who don't want to look at so many formulas as this, but there is a thing in mathematics called group, which abstracts various desirable properties of an operation on a set of elements, which is supposed to model multiplication or addition. And it consists of, classically, it consists of a set together with an identity element E of the set G, and together with an inverse operation I from G to G, and a multiplication function that takes a pair of elements of G and produces a single element of G, and then a bunch of axioms that, for example, maybe the most interesting one is the associativity axiom, which is the second one from the bottom. So what's novel about encoding the notion of group in type theory, and of course people have realized this for long, before Vladimir, is that you have to include the proofs of the properties in the objects when you're defining the type of such objects. And so whereas classically you would just have a sequence that has G, E, I, and M in it, and then settle for asserting the properties on the side in your English prose. In this formal language, the properties have to actually be included in the mathematical object. And once you include proofs of the properties in the mathematical object, then it becomes important to know that two proofs don't give two different mathematical objects. Mathematicians want associativity to be a proposition so that two proofs of associativity don't lead to two different groups. And this is ensured by his definition that a set has this property provided you impose this final condition, which is that G is a set. So groups make sense just as before when you do this. Now I want to show an example of a type of H level 3. This is the type of all triangles with unlabeled vertices. And I have three movies playing side by side. And the point of putting them side by side is that they share the same first frame and they share the same last frame. And so, and all of the frames in the movie are triangles with unlabeled vertices, every single one. So this is a movie in the type of triangles, or if you remember back to the Wikipedia page, we have three proofs of equality between two triangles in the type of all triangles. Now these three proofs of equality between these two triangles are different from each other. One can see that by focusing the eye on a vertex in the first frame and seeing which vertex it goes to in the last frame. The left one goes counterclockwise 60 degrees. The middle one goes clockwise 60 degrees. And the right one goes clockwise 180 degrees. So the vertices end up in different places. So these three movies are different, and mathematically, the three proofs of equality are different, and mathematically, the type of all triangles is not a set. So if there's one thing I would like everybody to go home with, it's this little image of how equality, which is a notion of logic, even in this logical system, incorporates from the very start the notion of symmetry of mathematical objects. This is something that doesn't happen in set theory. That's something that's built on top of the set theory by the mathematics. Of course, symmetry is important in mathematics. We study it all the time. And so I think it's immensely interesting that symmetry comes in right at the very beginning and can be used to motivate a lot of the theory. So there was the special year that Robert referred to in 2012-13. I came to that year and I found it super educational. I really needed an introduction to the subject that was intense like that. And the book was produced. You can download an electronic version or get a version on Lulu for $9.73 in paperback form. And the Foundations repository that Vladimir created lives on in the form of the UniMath repository, which Benedict Arens and I co-founded with him. And it incorporates that, and I hope to put a lot more theorems into it, and Benedict has also put a lot of theorems in it. Other people are contributing too, and if you think you can contribute, you're welcome to take a look and contribute. And there's the final lecture that Vladimir gave at a birthday conference for Per Martin-Löf, who invented the flavor of type theory that we've been talking about. And here's part of his abstract from his notes for that, or his final report for that talk. And I want to introduce this to explain to you what Vladimir has been working on since about 2013. Work on proving consistency of intensional Martin-Löf type theory with a sequence of univalent universes led to the understanding that in type theory we do not know how to construct an interpretation of syntax from a model of inference rules. So syntax refers to the parentheses and pluses and minuses and x's and y's in some sort of formal mathematical statement. And inference rules refers to the rules of logic. For example, one rule of logic is that if x and y are types, then there's a type consisting of the functions from x to y. This conjecture, that is, we now have the concept of a model of inference rules and the concept of interpretation of the syntax and a conjecture that implies that the former always defines the latter. This conjecture, stated as the statement that the term model is an initial category in the category of all models of a given kind, is called the initiality conjecture. And so this is the conjecture that he was working toward in the last 4 years of his life. And this is probably an important paragraph of the introduction. The first few steps in all approaches to set theoretic semantics of dependent type theories remain insufficiently understood. The constructions which have been worked out in detail in the case of a few particular type systems by dedicated authors are being extended to the wide variety of type systems under consideration today by analogy. This is not acceptable in mathematics. Instead, we should be able to obtain the required results for new type systems by specialization of general theorems and constructions formulated for abstract objects. So he was proposing this idea since 2010. He had the idea of building this in 2010, and sadly his work was interrupted by his sudden death. So here's one of the papers in the project. He had 8 papers submitted to 8 preprints, I should say, submitted to the archive during these last years on this topic. And here's one of them whose publication has been delayed by his death. The C system of a module over JF relative monad. Well, the words look pretty scary, but it's his dream that this will become a standard part of mathematics, and this will be the way that mathematicians of the future talk about syntax, those pesky symbols that you have to write from left to right on the computer screen in order to get your proofs into the computer. So this paper was refereed twice. The first time it grew from 20 to 30 pages, and the second time it grew from 30 to 60 pages. And we found it in his files, and we had to shepherd it into publication in some sensible way. It was not complete. Now, one more thing I want to mention is the possibility of doing mathematics, or rather topology, not with triangles, but with little squares or cubes. And so this is an example of a surface that has been tiled with little squares. Forget about the distances of the edges. This is supposed to be just a topological picture, but you see that it's intuitive that one could represent shapes also by little squares. And Vladimir had a conjecture about computability of type theory with his univalence axiom, which is really important because once one enters the world of type theory, one finds that this formal system supports constructive proofs, if you wish to phrase your proofs constructively, so that the proof can be run as a computer program and produce an answer. And so Thierry Coquin and his co-authors have developed cubical type theory, and it's looking like one of the most promising avenues for realizing Vladimir's dream about computation of the univalence axiom. And there's the proof assistant they promulgate. And to sum up, motivic homotopy theory is blossoming despite Voevodsky's change of focus about 10 years ago. Many dedicated researchers continue to find new ways to apply his fundamental ideas to algebra, geometry, and topology, and similarly, univalent foundations is destined to remain a vibrant area of research Formalizing Voevodsky's work on motives in the univalent foundations would close the circle in a fitting way and fulfill one of his dreams. Although actually later he did say in one talk that he wasn't so interested in formalizing his work on motivic homotopy theory because he was supremely confident of the results. However, what would be interesting, truly interesting, would be to make it constructive. And he mentioned a particular obstacle, a non-constructive argument, inherited from Merkuriev and Suslin, which would be good to eliminate. So there's a research project for enterprising mathematicians. And so let me end with a picture of Vladimir in his most snazzy sport coat at a latitude of 78.3 hunting fossils with me in Svalbard. Thank you for your attention.